level of significance, which is what I'm going to use to reject or accept the null hypothesis in that case. And it's the p-values you're going to use to do that. So what is it about confidence level of significance and all of that? You use level of significance to come to a decision, but having this parameter also, you can also get a confidence interval. So what do we say about confidence interval? You can say, okay, within this interval, I'm so sure that so thing is going to happen. So let me give you a case scenario. You can say, for example, let's say two teams are to play a match. You want to predict the number of goals that is going to happen in that match. Now, if you say 2 to 5 goals, 2 to 5 goals, mean I have maybe they should score 2, 3, 4, 5, 2 to 5 goals. That's 4 options. Compared to someone that said they are not just going to score 4 goals. You that said 2 to 5 goals, you have a higher chance of getting that prediction compared to someone that said they're going to be 4 goals in that match. It just has only one chance. They have to score 4. For you, they score 2, they score 3, they score 4, they score 5. So the person that said 2 to 5 is going to have a higher confidence interval compared to someone that just picked just one option, which is 4 goals. So the confidence interval for the person that picked 4 options is going to be high. You're going to have a more confident that, okay, this prediction should come to pass, to come true. So let me get a pen. Hold on, just 1 minute. So for example, I have this case. Let me use my whiteboard marker. Whiteboard marker. Whiteboard marker. Yeah. Just very fast. Okay. So for instance, say in a match, a football match between two teams, we have that A predicted that there's going to be 2 to 5 goals in that match. Then B predicted that there's going to be 4 goals. Now, you know that probability is between 0 and 1 inclusive, 0 and 1 inclusive. If probability is 0, it means there's no chance of it occurring. If probability is 1, it's a certain event, it's sure it's going to happen. Now, the kind of confidence interval this first guy going to have is going to be, so let's say this, you want to pick an interval within this range 0 and 1. If the confidence interval of this first person is between 0. Let's say 7 to let me use 2, 0.7, 0.9, 0.9. It is very close. The confidence interval of this person, because it just has only one chance, so the probability of this guy happening is going to be the confidence interval of this guy is going to be larger, because it's going to be probably going to be between 0.5 and 0.95, because he has a very slim chance of having this guy to happen compared to this guy. This guy, the confidence interval of this guy's prediction probability is going to be close because he has uh, different options, like 4 options. But compared to this guy that has only one option, so the confidence interval is going to be wider so that to be able to accommodate whether this is going to happen. So that explains that part. So moving forward, here, yeah, so let's conduct peer test and unit test on some data. Think that you have a file called KCD sample, which consists of MPD data, and the MPD data comprises of 2 samples, white and yellow. Carry out a peer-to test on this data. Carry out a peer-t test on this data. Start the alternative hypothesis. Set the alternative hypothesis that the difference in means is 1 and show the 99% confidence interval. So for the first guy, you just have to use the woocause.text command and specify uh, the column, the 2 columns. In this case, white and yellow. So I want to have something like this. So let me erase this. I'm going to have something like this. Say, vcons, I have vcons dot test. I'm going to specify, I think, white and yellow, white comma yellow. And these are the column, because you have to specify the data you're picking from. So data is equal to, I think, mpd.s. Then what else do you have to specify, which is important? Paired, the paired parameter. Sorry. I have to specify that the paired parameter, paired is equal to true. I can use just capital T or type capital true in full. So this is going to perform a Wilcox test, paired test for you. If you are doing the t-test, all things being equal, I'm going to specify all of this white, yellow, data is just MPDS, then paired is equals to true. Then what does you need to specify given that exercise? You are told that and state the alternative hypothesis that the difference in means is 1 and show that 99% confidence interval and show the 99% you have to specify. I think that's all you need. Is required. And what else? Conf.level is equal to 0.99. That is going to perform the second case. Okay, moving forward. Talking about correlation and covariance. So when you have two continuous variables, you can look for a link between them, which is called correlation. So how does this variable A affect variable B? Now correlation has value between -1 and 1. So that depends. If the value of the value of correlation is close to 1, you say the two variables are positively or strongly positively correlated. Then if the two variables are close to -1, then say they are strongly negatively correlated. Use the core function, CER function, to run to find the correlation between two variables. Then use the COV command to examine covariance. Can perform correlation tests using the cohort.test command. I think I have. Let me open another script. Don't mind this. I'm trying to run some web script in here. Let me open another tab. So let me call the array data set into this environment. So let me get the head. Yeah, the head of my data set. So as I was saying, if you perform correlation, say you have this. Say oh, so for example, say I have 2 data points and I want to check the correlation of both of them. So let me draw a plot. I have variable y and variable x. Now, if I have something like this, I would say this guy is positively, these two variables are positively correlated. But if I have it this or the other way around, then I would say they are negatively correlated. Both of them are negatively correlated. Now, in case of this first one that's positively correlated, you can see that increase in x causes an increase in y. But in the second case, where they are negatively correlated, you can see that a decrease in x, let's just say decrease, increase in x causes a decrease in y. Yeah. So I think I've already talked about this in the previous class, so I will just brush up and move on. So I think I've already spoken about this. So let me go to the third slide. I think I'm here. So talking about significant testing in correlation test. So if I want to do a test for correlation, is this is there a correlation between the variables or not? So if I'm doing a correlation test between two variables, here you use the cohort.test command to perform correlation test. By default, it performs the Pearson product moment, and you can specify if you want to do the spearman correlation. So you have the Pearson product moment correlation, you have the spearman correlation. So in case you're doing the Pearson product moment correlation in R, you don't need to specify method parameter. But if you are doing the spearman rank, then you have to specify that method is equal to spearman as another parameter in your function. So in this case, so if I'm doing the correlation test between two variables, say x and y, and you're gonna have something like this. If you're doing an hypothesis test, you have your H naught and you have your alternative hypothesis, which is can be your H1. So your H naught, if you're doing a correlation test, it's gonna be something like, say rho is equals to 0. This is gonna be your uh null hypothesis, because your null hypothesis assumes equality. Alternative hypothesis can be three ways, can go three ways. It can be rho is not equals to 0, rho is greater than 0, and it can be this, and it can be rho is less than 0. So 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 your H not saying there's no correlation, while H1 disagrees, say, oh, there is a correlation. So if you are rejecting the null hypothesis, it means you are saying that there's a correlation between the two variables. So okay, now here I have women height and women weight. I'm performing a correlation test between these two variables, and I have my results here. Don't forget, your p-value by default is 0.05. Your alpha. So you're giving the calculated p-value was given after you ran the command, and I have like this result, which is like 0.1.08 times 10 to the power minus 14. That's alpha less than 0.05. Since your p-value is less than 0.05, then what are you going to do? Null hypothesis? You're going to reject the null hypothesis, and you're going to accept this alternative hypothesis that says true correlation is not equal to 0, which means that there's a relationship, or there's a height and weight. So to buttress that, I think I wanted to write something. So yeah, so let me just go over that again. So for example, decision rule, decision rule, decision rule, decision rule. I've talked about it for some. Given your alpha, which is the level of significance to this, then let me just restrict it to a particular alpha. Given alpha, if your p is greater than alpha, you fail to reject. That means you accept. fail to reject H naught, which is your null hypothesis. But if it's the other way around, where P is less than alpha, then reject the null hypothesis, reject H naught, and accept the alternative hypothesis. Okay, so moving forward, yeah, oh, still the same thing. Okay, yeah, okay, yeah, you can see that the method uses Spearman rank, so I have to specify Spearman. Yeah, you have your S value calculated, so like your correlation and your test statistic calculated value, and your P value, which is the same thing you're going to use to come to a conclusion. So I think we still come to look, you're using another kind of variable, you're using speed and distance here. So here we're also rejecting the null hypothesis then because you're going to say there's a relationship between speed and distance, that there's a correlation between speed and distance. Okay, now moving forward, test for association. So for categorical data, users can look for association between categories by using the chi-square test. So routines to achieve this are assessed using the chi-square test, that is chi-sq.test command. And we have various instructions that you can add to this command, which are given below. Here, it takes particular x and particular y. Y can be null, like you may know of your y. So a basic x-ray test is carried out on a matrix of or data frame if x is provided as a vector. The second vector can be supplied if x is. So most of the time, in practice, you use a contingency table, which is kind of a matrix format to conduct your cascade test. So your y wouldn't be necessary in such cases. So correct is equal to if the data forms a 2 byte contingency table to perform the artist correction. So if your contingency table is a 2 by 2, then you should set it so that you get a warning from the command. So P, it's a vector of probabilities for use with a goodness of fit test. So if P is not given, the goodness of fit test that the probabilities are all equal, so everyone have equal chance of occurring. Yeah, you have the scale dot P before if true P is rescaled. So so moving forward, we can go through. I think this one and this, yeah, simple. About fit test. Why fitting it? Before I go into this, let me talk about the chi-square test. So, or first of all, let me try to do a correlation test with this guy. So I want to find the correlation between iris sepal length and sepal width. Let's check. Let's check that. Iris pattern, sepal length, iris pattern, sepal width. Sepal width. Sepal. You can see that one and 7. Let me just convert. Let me just let us let us do like a column. pair of matrix. Matrix. Let me do for the first column. I have a correlation matrix in this case. So if you see here, you can see that sepal length and petal length have a strong correlation. Also, sepal length and sepal width has a strong correlation. You can see the value 0.87, 0.81. You can see that petal width and petal length has a very strong correlation, 0.96, strongly positive. So sepal length and petal width have a very strong correlation. You can even investigate that to see. Let's do a plot between iris percent petal length, iris percent petal. No, why did I just petal? I make petal length and petal width. Petal, yeah. So if you look at it, you can see that the graph is going like upward in upward direction. That's why you have a strong positive correlation, as you can see on my screen here, 0.96, very strong. So it means increase in petal width causes an increase in petal length. It's very strong. So if you want to perform a correlation test between these two variables, again, I can say Cohort3, then I specify I want to do correlation test between these two this manner. So then you can see here product movement correlation. Degree of freedom is 178. This is that my length, the length of my this correlation testing. Just for the I don't know what Julian process.
I'm in the office. He's at home. He's at home. Okay.
Hello? Hello.
Ah, the mother died. Ah,
Yeah. I'm checking.
Let me see. Index and fruits. It's very 9,50,46. Zero, 10, 8, 6, 0, 0. Actually, can you hear me? So, right. So this is gonna have the number of rows here is gonna be
Sorted. Sorted. You're not very clear.
tell him that
Hello?
he should print
Can you hear me?
registration page
Yeah,
of
but
what
it's
he
not
Can you
too
hear
wanted
me?
clear.
the new
It's not too
LC.
clear. Let me go to a quiet place.
Okay, okay. All right.
Are we just two? Eh?
Are we
Hello?
just what? Are
Is
we
it
just
just
what?
me and Mary that are for
Hello.
this training?
Yeah, I'm Petra joined, but I was having connection issues that time, so I think she lost
Can't hear
connection.
you very clearly. Now. Hold on.
Black. Okay.
Sorry?
Okay. I wasn't talking.
Okay.
Uh, my um, right, tweet, tweet, mail, post, story, and something. Yeah. Then I have the row, the column name is going to follow. It is garden, uh, H row, pattern, struct, uh, and- yeah. So let me try and create the map. Yeah. So error, numeric matches explains. Uh, let me check again. I will go to this one, two. Oh, okay. Second. Ah, yeah. We have this. So these are the matches of species and habitat. So, so this is how it's going to look like. In log format, I'm going to have list of species, list of habitat. First thing, you have it. They're going to use the table command and say table into the the table like this for you. That is an association. So, the association question. Yeah, but there is those you get that say there is and as a man here emotion and uh, got similar value. What I have is similar. I say that there is a correlation between petal length and petal width. And even with the correlation value, you can see very high, 0, which is almost close to 1. So it means there is strong correlation between that is yeah, start to test how is greater than chi-state test, do a goodness of the test. And, uh,
I'm struggling to hear you guys. I can't even hear you guys. No, struggling. Hello. I'm struggling to hear you guys.
You're struggling to hear me.
Yeah, as in you're going in and out. Hello.
Yeah.
It's faint to. Hello. Let me disconnect and try connecting again.
Today, can you hear me?
Yes, I can hear you.
What did you say? You can hear me from here. Hello? Hello, today, can you hear me?
Yes, I can hear you. I can hear you.
Okay, it's better now.
Yes, better.
That's really not interesting. It's fine because I don't know what's wrong. Uh, let me use a laptop. Are you seeing this screen? Uh, Are you seeing this screen right now? Um, Can you see my screen?
Yes, I can see your screen.
Um, you- you- so that period I was trying to explain the chi-square test. So let me go by it again. So the correlation test here, I'm trying to do test whether there is a relationship between this guy, this variable height, and this variable weight. With this result, you can see if you don't specify the method parameter, you'll be doing the Pearson product calculation. You have the Pearson product moment correlation or the Spearman correlation. By default, it does the Pearson product moment correlation. And here you have a t value, you have a degree of freedom, and you have a p value which you use to compute. Come to decision with your p value. By default, your alpha, which is your level of significance, is 0.05. And whenever your p value is greater than your alpha, you are going to accept or fail to reject the null hypothesis. But if your p-value is less than your alpha, uh, you reject the null hypothesis, then you're going to accept this alternative hypothesis. Now, here we are saying that true correlation is not equal to zero. That is, there's a relationship between what? The two variables, height and width. And since you are rejecting the null hypothesis because your p-value is actually less than 0.05, you're going to accept the fact that there's correlation between height and weight with this test. Now, in this second example, they use the Spearman method, as you can see specified here. Also, we still come to the same conclusion with our p-value. You can also use the formula syntax to do the testing here, but you have to specify here. You're specifying the data that okay, I'm picking from this data, but I'm want to perform a test on speed and the distance column, and say okay, let me check is there a correlation between speed and distance, and we still come to the same conclusion with this p-value. Now going back to the test association. Now, hello, hello. Okay. So performing chi-square test. To use chi-square test for association, check is there an association or relationship between a particular column and a particular column. Usually categorical views, use categorical views. So I was trying to do some a test with two columns called habitat and species. So is there a relationship between species and their respective habitats? So we're trying to do that. So we perform a chi-square test, then we come to a conclusion given our p-value and say, okay, there is a significant relationship between these two columns. So what do you, or how do you do that? So you are doing a chi-square test. You have the observed value, and we have what we call the expected value. That's the mathematics behind it. Let me try that. Try to share from this my laptop here. Give me a minute. I think it will be better that way. I want to see whether I can share from my. Let's see that first. Let's continue. Okay. Sorry, I have to use. Yeah, I'll just use the system. So, so the mathematics behind it is called the observed and the expected. So, for example, let's say tossing of a coin now. I can, if I toss a coin 10 times, if I toss a coin 10 times, I can have like 7 heads and 3 tails. That's if I should toss it like me tossing it in real life. Like I have 7 heads and 3 tails. Like in those 10 trials. Now that is the observed value. But the expected value, what should be the expected value if I should show a coin 10 times? Can someone just tell me what is the expected value, like mathematically? What is the expected value I should get?
If you throw it coin 10 times,
Yeah.
you could either be head or tail.
Okay. So how many heads should I get? How many tails should I get?
You can get 10 heads, 10 tail. You can get 9 heads, 1 tail. You can get 8 heads, 2 tail. So there are so many.
I'm not talking about the possibility, like what is expected mathematically. So I just give you a scenario. I tossed a coin 10 times. Okay, I got 7 heads and I got 3 tails when I tossed it. That's observed because I observed it and that's the observed value. But what's the expected value? What's the expected result like statistically?
I'm lost on that, to be honest.
Okay, so statistically, okay, let me come in this direction. What's the probability of me getting a head if I should toss a coin?
1.
1 is one the probability of
Wait,
is
if you
one,
toss wait, if you toss a coin, how many times?
just tossing a coin just once. If I toss a coin once, what's the probability of me getting the head?
Twice.
Just once.
If you toss a coin once, the probability of you getting head is 1 now, 1/1 now.
So that is not correct because
Okay.
if I should toss a coin, okay, what are the options? What is the sample size? What are the possibilities I can get if I should toss a coin? Let me come that way. See that what? A head or a tail, right?
Yeah.
So the probability of me getting a head is 1 out of 2. That is 1/2. Also, the probability of me getting a tail also is going to be an equal chance, 1/2 too. So there's no cheating if it's a fair coin, right?
Hello, sorry, I didn't get that. You said the possibility of getting my head is 1/2.
Yes.
Okay.
And the possibility of getting a tail is also 1/2 because
Yeah, sure.
there are 2 possibilities, head and tail. So it's
Yeah.
1/2. 1/2. So it means half. They have equal chance, right? So if I should toss a coin 10 times, both head and tail should have equal chances of occurring. That means I'm expected statistically that I should have 5 heads and 5 tails.
5 heads and 5 tails.
You understand? 5 heads and 5 tails. That is what I'm supposed to have statistically by default because both of them have equal chance. But if you do it in real life, it might not be the case. It might not be the case. Wait, so, right? Am I
Yes.
making sense? Yeah. So it might not be the case if you do that in real life. Let me use the black white marker. So it means in the observed value, in the observed scenario, I have 7 heads and 3 tails. But expected value is supposed to be 5 heads and 5 tails. So this is what the chi-square test used to do the perform the test statistics and come to conclusion whether you're going to accept or reject the null hypothesis that okay, there's a relationship between 2 variables, or depending on what kind of variables you are considering in this case scenario. I don't know what's happening. I want to use the white marker so that I'll be able to explain what I'm talking about. Okay. You have asked the third here. You don't have it installed. Have you installed it?
Hello. Hello.
DJ, can you hear me now?
Yeah, I can hear you.
So
I can hear you. I can hear you.
sorry, I just lost maybe now. We use O. Your line is breaking. I can't hear you. Your line is breaking.
Hey.
Why is that happening?
What do I mean? If I do that in Sunday, I should.
Just call me when you do.
The network is not full. The network is not full.
Not every
Connect
day.
to. The network is not full now. Come and see. Hello? Chide, can you hear me? Per second. See me per second. See the line.
I can hear you.
Okay, your line was breaking before. Your line was breaking before. But you can hear me.
I can hear you. Yeah.
Okay, good. I think let me try and share my screen again whether I can share through my laptop now. Okay, so I was saying that my observed value when I tossed the coin was 7 heads and 3 tails. But what I'll be expecting is that it's supposed to be 5 heads and 5 tails. Yeah, 5 heads and 5 tails. So that's what. Can you see my screen? You can see my screen, right? Okay, good. So what I'm supposed to be expecting is 5 heads and 5 tails. So let me go to my drawing board and show you what chi-square does at the background. So the chi-square value is, let me go to my whiteboard. It's my mouse. So I have hold on. So I have something like this. This is my observed value. So I have observed 7 heads and 3 tails. Now my expected value is supposed to be 5 heads and 5 tails. So what chi-square does is that chi-square, this is the symbol to represent chi-square. You know, say is equal to observed, each of the observed value minus the expected value, all squared, all over the expected value. Then you take the sum. This is going to be your test statistics. This is how chi-square is going to perform your
Okay, so Expected value is 5 head, 5 tail.
Yes.
O is what again? Sorry.
Observed value.
Observed value.
Yeah.
Now,
So
are you just making these things up, or
I'm
so if
not
I
I'm not
toss a
making
coin 10, if I toss a
I'm,
coin 10 times, there's a
okay.
possibility I can get 9 head and 1 tail.
Yes, that's observed. That's if you toss it, you can toss it like just toss it in real life. Toss it.
Yeah.
Whatever you get at that particular point is what you observe.
Okay.
But statistically, what you are supposed to expect is equal number of heads and equal number of tail. Do you understand? Do you understand? Now
Okay.
let me give you another scenario. So this is one scenario. Another scenario is this. In a class of 20 students, for example, we want to record their marks. Are you with me? This is going to be the observed marks. Let me say observed marks. Now, maybe let me just consider 5 students because of this the space of this my notes. So let's say someone scored over 100, someone scored 60, and that person scored 56, and that person scored 70, and that person scored 75, and that person scored 90. Are you with me? This is the observed marks when they took the examination. Hello, Chude, are you with me?
I'm with you.
Now, the expected score you are supposed to expect, the expected score is equal number of marks for every one of them. You expect, statistically, I supposed to expect everybody to score the same thing, logically, because maybe they took their all human beings, so I'm supposed to expect the same score. So that is what.
I didn't want thinking they're all human being now.
So though in real life they are not supposed to have the same scores. Though there are some people that are based on people that are going to get like the same score, but all of them will not have the same score. But statistically, I'm supposed to have the same thing for everybody. So expected result is going to be the average of these 5 people. Let's say the average of these 5 people is 50. I'm supposed to expect 50 for this person, 50 for this person, 50 for this person, 50 for this person, 50 for this person. This is how chi-square is going to perform their expected values. So it's going to use this to calculate the test statistics and do the analysis and say, okay, whether this guy came from a is coming from a particular population or stuff like that. So, for example, I'm going to show you this in R, how this is being performed. Now, I'm going to go to R and give you the real life scenario and show you. Now, I want to create. Sorry, let me use the source. I want to use the first scenario, which is the head and tail. That's the coin part of it. So let me say my let me call it DF. I want to create two sample head and tail. So let me say, for example, I have 20. I toss a coin 20 times, and I got 12 heads and 8 tails. I have to store this value in DF. I've stored this. Now, my expected value is supposed to be 10, 10. So I will not write expected value. I will let R to find my expected value using chi-square. So then I will do chi.square. I will assign something. I'll say my chi-square is equals to chi.square chi-square dot test of df. So I want this. I want this. So I want to find the expected value that this is going to give me.
This one
How
is
do you?
mathematics, so
I'll say chi underscore square ampersand
this
expected.
R, this R.
Yes, this R. So by default, this is going to help you calculate the expected value. So this is the expected. Are you seeing it? So I click on chi-square percent expected. Let me see the expected value is going to give me. Can you see? 10, 10. So it gave me 10, 10 as the expected value. So it means the expected value is expecting it to have equal number. So it's going to use the average of both of them as what an expected value. The same way it's going to do for the case where you have scores and all of that. Now, another case scenario of this is this guy. This one I have matrix form. I was going to calculate the expected value of this guy. So let's say, for example, I've created the matrix already. So let me call the matrix for you. Bet.df. This is the matrix. You have this matrix. How is R going to calculate the expected value of this guy? Or how do they calculate the expected value of a matrix like this in real life? So if I should run the chi-square test of this, so let me first run it and assign it to a variable. So let me run it and say chi-square. Let me assign this to this. I've run this, so it gave me 180 to some low values I have in that matrix. So I'll say chi-square as an expected value. It's going to calculate an expected value for this same data frame also. So expected. If I should run it, I have a table value too. So this is my original what? Observe. This is my observed value. This is now my what? Expected value. So how did I calculate my expected value, or how did they calculate the expected value in chi-square? So I'll come back to the drawing board to tell you how this expected value is calculated if you have a tabular form like this or a contingency table. So I'll come back to my drawing board. I'll raise this. Yeah. So I'll just create a very small matrix, a 2x2 matrix, and tell you how it does calculation. So if I have a matrix like this, say 15, 20, 10, and 5. You have a contingency table of this search. These are the observed values. Now, these are observed values. So how do I find the expected value? Now, this is, I'll label this so that you don't get confused. This is in position. This, I'll call this 011, 012, that is 021, 022. That is value in row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. So how is it performing the expected value of this guy? Now, what are you going to do? Let me first remove this circle that is there. I'm going to sum this guy across rows and across columns this way, and the sum total. So I'll get sum total. So let me draw the tabular form like this. 15 plus 20 is 35. 10 plus 5 is 15. 15 plus 10, 25. 20 plus 5, 25. What's the sum total? 50. Right? Good. Now, how is it now going to find the expected value? So let me do this. So, yeah.
This one is mass.
You said?
This one is mass.
It's statistics now. It's statistics. So how is it going to find the expected value? So expected. So I'm going to have. So for E11, O11, this is the observed value. For E11, that is expected value in row 1, column 1, is going to be 011. Sorry, what am I writing? I'm very sorry. Sorry. The row total for column 1 and the row total for row 1 divided by the grand total. Now, this is the grand total. Let me erase this. This is the total for row 1. Sorry, column 1. This is the total for what? Column 2. This is the total for what? Row 1. This is the total for what? Row 2. 1, 2, 1, 2. And this is what? The grand total. So let me name it grand total. So to find E11, which is expected value in row 1, column 1. So E11 will be the grand total in this place, this one and this one, multiply it. So that will be 25 times 35 divided by the grand total, which is 50. Now for E12, that will be corresponding to what? The total here that corresponds to 012 and the total that corresponds to what? To the row of what? 012. That will be 25 also times what? 35, then divided by also 50. Now for E13, no, sorry, E21 rather. What's the total that corresponds to 021 here on the column level? 25. What's the total that corresponds on the row level for 021? That's 15 for 021 divided by what? The grand total was 50. Now for E22, what's the total that corresponds to the column? 25. What's the total that corresponds to the row? It's still 15 divided by what? 50. So for this guy, if I do a calculation, this is going to give us, well, I have 10 missed calls already. 25 times 35 divided by 50, that's going to give like 17.5. It means this one will be 17.5. For the second one, 25 times 15 divided by 50. This is going to be 7.5. And this is going to be 7.5. So it means our expected value is going to look like this: 17.5. This one also be 17.5. This one is going to be what? 7.5 and 7.5. Sorry. So this is our observed value, our expected value rather. So we have observed value to be this, and we have our expected value to be this. So it means in 011, I expect 011 to be 17.5. I expect 012 to be 17.5 also. I expect 021 to be 7.5. I also expect 022 to be what? To be 7.5 in that regard. So that is how expected value is calculated if you have a table like this. So let's go back to ARC and compare what we have. So if you look at this, say from this guy, we are calculating what? Our expected value, which is this. So let's now find the row sum and the column sum. So if I want to find the row sum of this table, I'll use the function called row sums. Row sums. Then in the bracket, I'll pass the table bed d.df. These are the row sums. If I want to find column sum, I'll say call sums in this format and say bed df. .df. What happened? Call sums. So error in call sums cannot find function. Okay, so I use for capital C, not small c. Yeah. Now, so let me call this bed df again so that you can see and compare again. What's on my mouse? So these are original what matrix. This is let's calculate the expected value for this first guy, which is like 011 in this case. What's going to be the expected value? That will be the first sum on the row, which is 101 times, let me put it in bracket, multiplied by the first sum on the column, that's what? 175 divided by what? The grand total. So I'll just take sum of what? Bed df. This is going to give me the grand total divided by the grand total. So let me run it. Can you see? 59.91525. So what do we have in our expected value? 59.91525. The same thing. So you can see that that's the way it's calculated what the expected value in this place. So you can see that it's the same thing as what we have here. So I think we already understand how that is being calculated. So with that, we already understand the concept of chi-square in that regard, so we can proceed. I hope that's clear. Okay, so I think we should be able to wrap up this now. So here we have the summary of what we've talked about today. So statistical hypothesis is an assumption made by a researcher about population of data collected for any experiment. So the hypothesis is the formal way of validating the hypothesis made by the researcher. So I can make an assumption that okay, the average age of students in Nigeria is 20. That's my view. That's my assumption. Then you can validate that guy by collecting some sample of students in Nigeria and come to a conclusion. So another person can say, oh no, I think you are wrong. I think it's greater than 20. I think it's less than 20. Then I can collect some sample and do my test statistics and come to conclusion that no, I'm rejecting that null hypothesis and saying that okay, the average age of students in Nigeria is actually uh, less than 20. So we have hypothesis can be categorized into two types: the null hypothesis and the alternative hypothesis. So the null hypothesis is the assumption made by the researcher, and which is what we were going to test against using the alternative hypothesis. So null hypothesis assumes equality, while the alternative hypothesis takes the other way around. And we have what we call directional and non-directional hypothesis. So let me go over that again before we wrap up. So we have a null hypothesis assume equality. So let's say for two samples, so say I will have two samples, say sample A and sample B. Sample A and sample B, for example, I can have the null hypothesis is going to look like this: that say the mean of A is not different from the mean of B. The alternative hypothesis can be this, can be say the mean of A is not equal to that of B, is significantly different from that of B. That's the way you say it. Then, or you say the mean of A is greater than the mean of B, or you say this. It's either of these three, not all of them. The mean of A is less than the mean of B. Your null hypothesis takes equality. So this way is going to look like. Now, this first one is what we call non-directional. Why these two are directional? Why this one is non-directional is that it is not equal to. So not equal to, you can go to you can either go to the right or to the left. So if you are saying not equal to, it means it can be greater or it can be less. It doesn't have a direction. So that's why it's non-directional hypothesis. But when I say greater or less, then it's more directional. It's directional in that way. Okay. Also, yeah, so talking about two types of error that can result from hypothesis test, you have the type 1 error and the type 2 error. Type 1 error is when you reject a true null hypothesis, while the type 2 error is accepting a false null hypothesis. So let me give you a real life scenario of that. Say for instance, someone was charged to court and was accused of a particular offense. So suppose that person was innocent and the judge actually sentenced the guy to life imprisonment or was sentenced to death. Remember, the person was innocent. You said the judge just committed a type 1 error. You said the judge just committed a type 1 error because the judge rejected a true null hypothesis. But the person was innocent, but he was actually charged guilty for it. But the other way around is when the person was actually guilty, but the judge actually set that person free. So in that case scenario, he said the judge just committed a type 2 error. Okay. That is statistical test bit now talking about the T test and the U test. T test is a parametric data, a parametric test, while the U test is a non-parametric uh, test. Now we can use it to compare two samples or one sample. You can have a one sample test or a two sample test. In each case, for the t test, you use the t.test command to perform that test, while in the u test, you use the wake-up.test command to perform that test. And you can also have a peer test. A peer test, when I say peer test, it's not that it's different from what I just talked about. It's just that if you are performing a peer test using a t test or a u test, you have to specify a parameter called paired, P-A-I-R-E-D. So you specify paired is equals to true if you are performing a peer test. And when do you perform a peer test? Say, for example, you have the results or the scores of some set of students for first semester, and you have their score for second semester. And you want to check, is there a significant difference between their score in first semester and their score in second semester, because the two are related. So you're going to use you're going to you are doing a peer test in that regard. Then if you are doing that, if you are using the t-test command, you are performing a student t-test, then you have to state the parameter paired to be equal to true. You are trying to see whether there's a relationship or there's a difference between the score of students in the first semester and first semester and second semester. Okay, I think I've talked about a lot of things. You are all encouraged to go back to our material and also read. I will encourage us to do that so that you can also be carried along, because I've talked about a lot of things. I think I already thought this last week. I just have to come back and brush it up. So we are going to be continuing from this next session next week. This next session next week. So we also talk about
tomorrow.
Yeah, we have a class tomorrow. Yes, 12 to 2. I'm sorry, 2 to 4 rather. 2 to 4. So we also have correlation test. We have basically we have these two, but you can be talking about. I don't think how has this. So basically, these are the two common ones, which is the Pearson product moment and the Spearman rank. That's what they call the Spearman rank correlation. So we also have the core command, COR command, to find the correlation, the relationship between two variables, and you have the cov command to search for the covariance of two variables. So core command, which is correlation, find correlation between two variables, is the values of correlation is between -1 and 1. -1 and 1. So if your value is 0 or close to 0, you say there is no relationship between those two variables. But if it is close to 1, you say there is a strong positive correlation. But if it is close to -1, you say there is a strong negative correlation. When there is a strong positive correlation, you can say that the increase in the value of a variable x. So the ideal correlation that is between two continuous variables. Don't forget that, between two continuous variables. So if the correlation between those two values is close to a positive one, you say there's a strong positive correlation. That means the increase in a particular variable causes an increase in the other. But if there's a strong negative correlation, then you say the increase in a particular variable caused a decrease in the other variable. So for example, an example of a strong positive correlation is like maybe let me use height and weight. So it's most likely that the higher the taller a person, the higher the weight that person I think accumulates. Yeah, that makes a lot of sense. And I can also say maybe the one that is maybe kind of there is a strong negative correlation is when I'm saying speed and energy. First, speed and energy. Speed and energy. In this context, let me paraphrase it. So if you are in a race, you are running, the more you the more time you spend running, the less your energy, your energy is keep reducing as you keep running because you are exhausting energy. So the higher you even increase the speed, the lower your energy. So, so we are okay, Chide, thanks for coming, Mary. Thanks for coming. I hope we all get one or two things.
Thank you.
Yeah, yeah, you're welcome.